Hello, everybody. Okay, so the story of how stars are born has several steps, right? And so there's several moving parts. It's not the simplest, most straightforward story because there are multiple moving parts going on here. So let's see if we can put this together, right? You start with a giant nebula, right? A molecular cloud, right? A nebula of cold gas. And the mass of all that gas causes it to collapse under gravity. And the gas is not likely to be completely smooth, right? It's going to have some areas where the gas is more dense, and then some area, let's say, there's more gas here, and there's more gas here, and there's less gas in between, right? So there's going to be some lumpiness to it. And then each of these lumps, each of these regions where the gas is more dense, well, if it's more dense with gas, then gravity's going to be stronger there. And then this clump is going to collapse in on itself, and this clump is going to collapse in on itself, right? Each of the areas where the gas is more dense collapses under gravity, and then the area in between, where there's less gas, gravity is weaker. And so the gas gets pulled from where it is less dense to where it is more dense. It's going to be pulled from where the gravity is weaker to where the force of gravity is stronger. And then what it means is that you've got these, clumps of gas that are still collapsing. And then the area in between where there's less gas, it gets drained of even more gas. And so each of these lumps becomes even lumpier, right? The fact that the clumps are collapsing under gravity, that's hard to see in the camera, isn't it? But it's on your page, you see it. Gravity pulls everything together so that the lumps of gas get smaller and denser in time, right? And then each of these, a big clump collapses and becomes even lumpier, so it becomes a bunch of smaller ones, which become a bunch of even smaller ones, and so on, right? And then each of these little clumps of gas collapses and then forms a star, right? And then each of those clumps collapses and forms, I should say, the protostar with the protoplanetary disk of dust and gas around it, until eventually the protostar collapses down even more, until the core of that protostar goes over 10 million Kelvin, and 10 million Kelvin is the magic number where the hydrogen is finally hot enough to start fusing into helium, which then produces the radiation pressure to bring gravity into balance, establish your hydrostatic equilibrium, and your protostar has become a main sequence star, right? Until that happens, right? Until the nuclear fusion has started and is producing enough radiation pressure to balance out gravity, gravity is stronger than pressure, right? Gravity is pulling those giant regions of gas to get smaller and smaller and denser and warmer and warmer. And even though it's heating up, even though that protostar is heating up, gravity is still stronger. Gravity is still pulling it all together until finally fusion starts. And then there's enough fusion, just like when we talked about star structure, right? When there's enough radiation pressure pushing out from the star to balance out the gravitational pull of that mass coming in, then when they come into balance, then your star is born, right? Your collapsing ball of gas has finally become a main sequence star, right? So, are these true or false, right? Each giant molecular cloud produces one star. No, never, right? Because you've got these giant, again, they're called giant molecular clouds because they are dozens of parsecs in diameter, right? These are big regions of space with lots and lots of mass. and each of those clumps then collapses and becomes smaller and lumpier and smaller and lumpier, and then each of these little lumps forms a star. You never form one star at a time. Stars are never born one at a time. Stars are born out of those molecular clouds hundreds or thousands at a time. Large stars only form from extremely smooth fragments. Well, yeah, that's kind of true, right? Because if you have this big blob of gas, and if it's not that lumpy, right? If you have this, if you've got two blobs of gas and one of them is pretty smooth, and another blob of gas that is has lumps in it, and each of those lumps is denser, but then the gas in between is less dense, right? Then where's the gravity going to be strongest? Well, the gravity is going to be strongest in those lumps of more dense gas, and then that's going to siphon the gas away from the region around it, and those lumps become lumpier, and then each of those lumps becomes their own star. If you have a big blob of gas that's smoother and not lumpy, then what's gravity going to do? Well, gravity's just going to pull that all in toward the center, and it'll collapse and form one star. And that star will have the mass of the whole blob, whereas this blob over here could have started out with the exact same mass as the first one, as the smooth one, but then because the mass was less smooth, because it was lumpier, you're going to form multiple stars, but each of those stars will have less mass. So yeah, how do you form large stars? You form them from big, smooth blobs, and you form larger numbers of lower mass stars from lumpier blobs of gas. A protostar is fusing hydrogen into helium. No, not yet, right? The protostar is still collapsing. It's still heating up. It hasn't started hydrogen fusion yet to become a star. A protostar is a star. Yeah, kind of not. I mean, what do we mean by a star? Well, if you want to get really technical, right, a star is powered by fusion. And the fusion hasn't started yet. So it's warm, it's glowing, right? Why is the protostar glowing? Because the gas is heating up, right? Gravity is pulling that gas smaller and smaller and denser. And when that ball of gas gets smaller and denser, it's going to heat up and it's going to glow. It's going to glow with a continuous spectrum, just like any hot, dense object does, right? So it's glowing with heat, but the heat is not coming from nuclear fusion. It's coming from just the collapse of gravity. And so a protostar is not a star yet. When the fusion starts, the star is not yet a main sequence star. Yeah, that's true, right? When the fusion starts, the star is going to start making radiation pressure, but when the star first starts making radiation pressure, gravity is still stronger. And if gravity is still stronger, then it's going to collapse down more and more and more, and then heat up more and more and more, and that's going to drive more nuclear reactions and make more radiation pressure. So when the hydrogen fusion starts, it's not quite a main sequence star yet. Right? The fusion starts, and then once enough fusion is happening that the radiation pressure comes into balance with gravity, then it becomes a main sequence star. And that takes a little bit of time. Right? Planets begin to form when the star begins nuclear fusion. No, not quite. You can start forming planets. You can start forming protoplanets, planetesimals and protoplanets. You can start forming things that, chunks of rock and ice in this disk. You can start forming what will eventually become planets while the star is still a protostar before the fusion has started. So the process of starting planets begin to form before the fusion starts. Yes, that's true. Right? The process of starting planets starts while the star is still in a protostar phase. The protostars produce strong winds. That's true, right? Because that's where the jets come from, right? As that protostar shrinks down and heats up, that hot gas is going to blow out that wind. It's going to shoot out those jets until eventually that wind calms down and the protostar becomes a star. All right. So what's the whole story here? Let's put all these things together, right? You begin with a molecular cloud, right? A cold nebula with a lot of gas. It's mostly composed of what? What are the two main gases that make up basically everything in the universe? Hydrogen and helium. It helps if there's some kick, some jostle of the gas, right? Because a cloud of gas will, happily sit there, out there in the galaxy, and it'll collapse under gravity, but really, really slowly, right? There's a lot of mass in these giant molecular clouds, but they're huge. Like I said, dozens of parsecs in diameter, which means at the very beginning, this gas is so thin, so diffuse, so low density, that gravity pulling it into collapse is very slow. So it helps if something jostles that gas. Give that gas a kick. Something to poke the gas and cause it to become more dense, because if you can cause that gas to become more dense, then gravity will take over and cause it to collapse down faster than it otherwise would have. What could give a kick to the gas to get it collapsing faster? Well, one thing that could do that is a supernova. Right? If a supernova explodes inside the nebula, or right next to the nebula, then that supernova explosion will shock the gas and trigger it to collapse faster. After the kick, the force that dominates and causes the gas to collapse is gravity. The gravity takes over. Because the cloud is clumpy, it begins to fragment into smaller pieces. The pieces will form a group of stars called a star cluster. Right? A star cluster is a bunch of stars that are all right next to each other. Why are the stars all right next to each other? Why are they near each other? Because they were born together out of the same molecular cloud. As each fragment collapses, it decreases its size. It's going to increase its density and temperature. At this point, the fragment is a protostar, right? Each of those fragments collapses down and becomes, starts heating up, right? Because it's shrinking and getting more dense, it's going to get hotter. Eventually, it's hot enough that it starts glowing. First in the infrared, right? As it heats up, it's going to glow in the infrared and then eventually in the red. And now once it starts glowing and you can see it, then it becomes a protostar. That object's going to have strong winds and jets. The winds and jets are still mostly hydrogen and helium, because that's what the gas was made of. That's what the star is made of. Once the temperature in the core of the protostar reaches 10 million Kelvin, fusion begins, and the object becomes a star, right? Because a star is powered by fusion. So once the fusion starts, it becomes a star, but it takes a little while for the light, the luminosity, the radiation pressure from that star to bring gravity into balance, at which point the object becomes a main sequence star. And you have a fully matured adult main sequence star. There you go. That's how you go from, we're doing it in 10 minutes here, but it takes millions of years, right? It takes millions of years to start out with a giant cold cloud of gas, and then eventually let it collapse down, get warmer and warmer and clumpier until the fusion starts, and then the fusion balances out gravity, and then you finally, a few million years later, have a fully matured main sequence star. And as long as there's hydrogen to burn, right, as long as there's hydrogen to fuse, that main sequence star can maintain the hydrostatic equilibrium, keeping gravity and radiation pressure in balance, and it'll just stay like that. It'll stay as that main sequence star until it runs out of fuel. All right, so that's the birth of stars in a nutshell. All right? Okay. If that's making some sense, then get on to the practice, and then on to the next step in the lives of stars. I'll see you then.